Okay, this is gonna be kind of like a status report of Quxlang, what works, what doesn't work, and kind of just, I want to do like a little vlog here. Is this a vlog? I don't know if this counts as a vlog. I'm not using my camera. But anyway, what I want to do kind of is go through the code just a little bit and talk about what's working, what's not working, and you know, how far along Quxlang is to being usable. So I'm going to do some demonstration just to show you guys that this, it's not quite ready, but it is not a vaporware project either. And so for example, here I have these expressions that we're going to get with the const_bool function. This creates the expression here by the parse expression function, which just parses the expression, and then we actually call get a const_bool, which is just the expression plus the context. So that's basically where the expression would occur in the program. In this case, we're executing it in the context of the main module. And then there's this macro for the test data path. That could be a command line argument, but for now it's just hard coded as in the CMake configuration to be the test data path. And that points, so we have our main test here. And this is actually the language source code for now. And it's in the sort of this example directory, and it has the quxbuild.yaml file. In this, we define the targets. So for example, I have the Linux x64 target, which is the one that we are using in the tests. And this, we have our modules, and then we have, for example, the platform and the CPU. So basically you define your modules in your build file. And the idea here is that you could have more than one version of a module. So for example, in this example, I have barlib version 2.0 or 2_0. And for this target, which is the 64-bit, we're actually using a different version of barlib. So that's the idea. So this will decide what barlib is for the entire program. And this is what is known as a source module. And I believe this is what we call a build module. So the source module location is basically the source code folder. And then the build module is what it is known through the entire program. So this is actually kind of the canonical name inside the program is going to be barlib. So as a result, you can use different versions in different things. And of course, you also have the ability to do outputs. Now that doesn't currently work because I removed the code generation in the process of migrating to IR version 2, which is still a little bit under development. So unfortunately, there's no code gen for IR version 2 at the moment, but it will use the same syntax when it is implemented. And so, for example, you could create your output, decide what its name is, and decide what the main module is. Different things could go in here. So you could create more than one app in the same target. So these top level things are known as targets. And the target basically is all of the source code, but you can generate multiple different binaries from the same target. Now the goal here is that basically you would not have to recompile libraries that are used in multiple different binaries, for example. So it's kind of like a little bit like some of the advantages of traditional shared libraries, but with more static linking, or there might be some dynamic linking, but the dynamic linking would be limited to kind of dynamic linking in something that was essentially statically compiled, where it might be using the hash of a library version to determine exactly what binaries are in it, something like that. So anyway, that's a little bit into the future for now. But this is the module file, and the goal would be at some point to support other languages. So for example, you'd be able to have not only the Quux modules, but also C++ modules. So I'll go ahead and navigate to this build file here. So for now, that's not supported. It only takes one, but you create your module, and then you have the sources folder. And there might be things other than sources. For example, you could have binaries. For example, for linking in a proprietary project, there might be a folder called binaries that we could use to bring in some binary dependencies of the build. But here's one of the sources for this. And currently there is no, again, there's no code gen at the moment. There's just constexpr, which is, I'm trying to make it a fairly featured constexpr. So for example, we can execute these functions here. So for example, this test is validating that biz with 4 and 3 as parameters is equal to 18. So I can go in here, find the biz function here, right? And it's got 2 parameters. So these are positional parameters with the percent sign. You can also have like a named parameter. So for example, you could do at input, and then that would be a named parameter. And you could also name it like A. But the at sign would be a named parameter instead of being positional. And that mostly works, I think. So here we go. Variables are declared. We sort of declare the variable, and then the type is afterwards. If you want an array, for example, you can do brackets 3 like this, and that will create an array of size 3. And then it'll be of 3 i32s. So this is 3 i32s, or an array of 3 i32s, or 32-bit integers. And the assignment operator is different from C and C++. So we're using this colon equals. And the reason why I've done this is that I've seen a lot of code, especially when I was a new coder, I would do like this. And then I would wonder why the statement was always false, for example, in this example, or always true, depending on what you set the value to. And what I really meant to do is 2 equal signs like this. But by using 1, I had actually changed the value inside the if statement. So to prevent that kind of error, I'm adding a colon to the equals operator for assignment. And you will still use 2 equal signs for checking for equality. But this is just a nice thing that some languages have, where they make it a little bit impossible to accidentally do this, where you're creating an assignment in the middle of your if statement. So that's one of the changes that has been made to the language versus C and C++. Now, we'll also notice that pointers are actually using this sort of arrow operator, and there's actually more than one kind of pointer. So you'll notice that we have this single arrow, and then we also have this sort of double arrow, which is a equals like this. My IDE kind of combines them as with ligatures, but it is an equals and then 2 greater than signs, and that is an array pointer. And this is an instance pointer. And the idea behind an instance pointer versus the array pointer is that an instance pointer points to one object, or it might point to null. So it could be a null pointer. But the array pointer, on the other hand, points somewhere within an array. And what this means is that if I want to do array arithmetic, I want to add to a pointer, for example, I want to add 1 or subtract, I need to use an array pointer. Because if I have an instance pointer, that actually only points to one object and not the array, essentially. So you can't add to something in an array pointer. Or sorry, in an instance pointer. You can't add to an instance pointer or subtract to it. You can only check if it's null. You can do comparisons, or at least you will be able to. I haven't actually implemented that yet, but you will be able to check, for example, if it's less than or greater than something else, but you wouldn't be able to add to an instance pointer. And the reason why is that an instance pointer really is meant to point to one object. And the goal of the instance pointer is that if I call a function, for example, that writes to one of its arguments, but I pass an instance pointer, I can then make some assumptions about the correctness. For example, I know it's not going to go and modify an adjacent element, right? So if I have a function, and that function looks like, foo function, if I can spell function. So we have a pointer to i32. This function might modify a. So let's say it goes to a, and then it adds 1 to it, right? This is how we do reference pointers. By the way, we use this arrow. This is for instance pointers. But I know that it's not going to modify the value that is, for example, like next to it. And I can reason about how a function that takes an instance pointer behaves. And the ideal scenario is that we can introduce some compiler optimizations based on assumptions of the interface. So for example, if it takes an array pointer, it means that that function is not able to go in and start modifying other stuff that's not reachable to the function, right? So this wouldn't make, the values adjacent to that array cell reachable. Whereas if we have the pointer like this, we could say a0 plus plus, or we could add like to the value after it. So you could do like this, just like you would in a more traditional array. It also works that way for the array pointer. Okay. Now, there are some other changes from C and C++. So, for example, the way that we take a pointer to an object is a little different. So there's kind of two ways that we can take a pointer to an object. So you'll notice that we have this arrow pointing to, for example, z.x here. And that is actually the same as in C. This would look like z, like ampersand z.x, right? We're taking a reference. But this is actually just a pointer to z.x. So the way that you can think about this is that if we have a pointer and we do this, it sort of gets the value by the pointer, and this does the opposite. It gets a pointer to the thing. So these two like cancel each other out. So for example, and this is a dash and a less than or greater than sign, by the way. My IDE has ligatures, so it kind of combines them, but it's dash greater than with no space between them. But you can see that if we take a pointer, we do like that, that is getting the value pointed by something. And then if we do this, it's getting a pointer to that location from a reference. So in this case, this is assigning the A, which is a pointer to i32. It's saying it is equal to a pointer to z.x here, right? Okay, so that's how that works. The other kind of way that we take a reference is instead of accessing the element of an array, you can do this thing where there's an ampersand. And that sort of may remind you of the ampersand in C and C++ where we take a reference to something. This is getting an array pointer from an array. We're getting a pointer, an array pointer, to the 0th element of the array. And it might be the case, I might add something, for example, for the special case for 0 where we could do like this. I'm not sure if I'm going to do that or not, but this would be like an array pointer to the 0th element. Currently, that's not added. But like this would be a pointer to the 0th element of the array, which is something that you can do. And yeah, so that's kind of how you would do that if you want to do this. So you can get a pointer to the 0th element of your array with this expression. Now, another change that has been made to the language versus C and C++ is pointers do not automatically convert to a Boolean in an if statement, for example. So you actually need to use this double question mark. It's the same thing for integers. If you want to check if something is equal to 0 or null, you need to use what is called the booleate operator. So the booleate operator is checking if this is not null, or essentially if this has a value other than null. And there's also what's called anti-booleate, which I think is exclamation question, but it might be the other way around. Is it question exclamation? No, it's this one, which is just the same thing but the other way around. And the question will check if it's equal to null pointer or if an integer is equal to something other than 0, right? Or, well, this checks if it's not equal to null pointer, I should say. So this is essentially a conversion to Boolean for this pointer. Now, you'll also notice that there's no constructor in this class, and that is because by default, everything in Quxlang is 0 initialized. So this is different from C and C++, where I would have to set a default value. But in Quxlang, there is an implied zeroing of the class when you create an object of type int, for example. It will automatically be 0 without you having to say that it equals 0. It's 0 by default. Now there will be a way for performance critical code, for example, you'll be able to do like var x I32 equals probably like poison, something like this, to kind of correspond to like LLVM's poison concept of undefined. And this would essentially create an uninitialized variable, or you could probably do something like this maybe. I32 equals, unspecified. Now, these would be slightly different in concept. C++ would be equivalent to this, and there are some pretty significant consequences that I think people don't realize about how uninitialized variables work, particularly when a variable is uninitialized on a page that is not initialized on some operating systems. If you don't write to a page, its content can be kind of questionable and change from one reading to the next. So there are some pretty significant consequences that I think a lot of people are not aware of. It's not just a random value. It can actually just change from one time being read to the next. So that's worth noting. But hopefully those kind of mistakes will be a little bit harder, because it's not like you won't be able to have uninitialized variables. You'll just have to sort of opt into the behavior that you want. For example, var x equals unspecified, or var x equals poison. And then you can kind of get that behavior. So it's not you're not going to have to go too far out of your way to get that, if that's what you want for some performance related reason. But we're changing the default here to be a little bit more sane and a little bit less error prone. All right. Now, these are the main things so far. So I'm going to go ahead and execute just to show you kind of this can execute some stuff, and you can see it actually executes these sort of expressions here. This takes a second, mostly because of the print statements. But yes, as you can see, I'm printf debugging here. But I've got some different like instructions in the IR. You can actually look at this. So this is kind of part of the IR here that gets generated, and it for one of the functions here. So this is the biz function here. Let's see if I can find it. Right. And we create locals, and there is detours section. So for example, if there's a value that has a destructor, it will say which destructor is being used for the given type. So you can create a destructor function and say that this type uses this destructor object or destructor function. And it creates a whole lot of locals. There's a lot of different locals, and that's because each one is actually being used only once, basically. So, for example, it's not going to reuse a local between two different expressions or temporary. So there's a lot of them, but that's going to usually be optimized away. So it does keep track of which locals are currently alive. So, for example, this is the state comment, which is related to something called the state engine, which basically tracks which locals are currently alive and which ones are dead. And that's mostly useful for sort of stack-based virtual machines and some optimizations that can be introduced later. But the S here means that it has storage allocated, and the A means it has a value that's like it's alive. It's not just something with storage. So sometimes we may have something with storage allocated, but without a value. And for example, this is probably, given that this is number one, that's probably like the return parameter. Yes, so we can see that this is the return parameter. There is not really a concept of like a return. It's just an argument that is of type new reference. So basically an argument that needs to have a value written out to it, which is something that will be optimized sort of away by the compiler. Like if it sees that there's a type like i32 as your return argument, you can kind of, that can be optimized out as an actual return, in the code gen, if there's only one of them at least. Now, if there's more than one, obviously one of them has to be a pointer, but if there's just one, then we can sort of optimize that into a return, assuming that this is a type that can be sort of returned by value. Now, there will be types that can't be returned by value, but those already get turned into pointers anyway in C++, for example. But that's how that works. So we have a lot of different instructions here. For example, we'll go to one of these. So this is jumping around. So at the start of the function, we have storage for the return, and then we have two values. These are the two arguments that are provided here, arg A and B. And it'll jump around. It does load constant 0, so this zeroes out something. So 4, I think, is a variable, probably. And for example, we have make reference, cast ref, I think, yes. And load constant, access array, load constant, cast reference, store, jump. This will, for example, automatically run destructors. So if we jump from one block to a block where a value is not alive, now in this case that didn't really happen, but if you were to, for example, do that, it will like call destructors for temporaries, and if the type has a custom destructor, which you can go check, over here it lists what types require a function call or a procedure call for their destructor, and what types don't. So the functions do consume their arguments. For example, the store instruction is consuming, or these instructions, a lot of the instructions consume their parameters. So for example, this consumes 20 and 21. So it's taking, I believe, this value and storing it in the pointer, but it actually kind of deletes the argument from the state. And this can hopefully allow some like optimization and tracing, by sort of minimizing the number of active stack variables for like JVM as the backend. Now with LLVM, it's probably not going to be that big a deal because it's probably not going to take advantage of this. But for like writing a custom JVM backend, this could be useful. So we are going to focus on LLVM first, though. So I'll just quickly show that this actually works by changing this. So for example, we're going to assert that this is equal to 19 instead of 18. And we're going to run this test again, and it should fail. If it ever compiles. Well, not exactly quick. This computer doesn't have very much RAM though. All right, so it failed the test as expected. So we can go ahead and go to our test here. Now we're expecting the answer to be 19, but it wasn't, so I'll just add 1. We'll run it again, and it should probably still fail because I think there's another thing that uses that function. No. Is 4, 3 equals 4? Why did it pass? What? Oh, assert false. Okay, well, that would always fail, regardless of what it is. Okay, so, okay. So it's expecting it to be 19 here. And it is now 19. I just changed the value in the code. It executes the const expr. And it can, for example, execute the const expr instructions inside of like a array brackets. See if I had that anywhere. Don't know if I do. But we could, for example, do 4 plus foo bar like this, or let's do 3 plus foo bar. And then we can say foo bar. Yeah. You could do this if we want. And this will compile, and it will execute that function, or it should. Didn't work this time. Why did it not work? Expected uint 60. There's some rough edges right now that will be fixed later. One of them was that it was expecting a 64-bit integer because that's the size of an array on that. Right. So just zoom. What? What did I do wrong? Oh, yes. I have not implemented i64 constructor. What? Why is it trying to create a what did I do wrong? Oh, yes. Yeah, there we go. So some implicit conversions still need to be added. There we go. So as we see, this worked fine, and it was able to call this function and create this array. And we can actually see that it executes this, hopefully. Yep. So it's looking up this type, and it actually executes the expression to resolve the type and figure out what this type is. So it's trying to figure out what this type is in that context. And it executes the expression in constexpr, and then it gets the value, and then it decides what the type is. So you might be wondering how that works. And in fact, the order that we declare these things is completely irrelevant. So for example, we could declare this down here, and it won't care. This is very unlike C++, for example, where it very much cares about the order you declare things in. This language does not, so you never need to declare, for example, forward declarations or anything. And we can kind of get a glimpse of how that works based on coroutines. So this uses a resolver function system. There's a bit of macros that will eventually be refactored out. But for example, we're awaiting on the overloads for something. And there is a solver. So there's a single thread solver, single thread graph solver. And there will be a multi-threaded one later on, but this for now is a single threaded. So it's going to try and call this solve function. Which one of these is it? This one, perhaps? Yeah, so it's got a list of nodes that haven't been solved, and they these nodes basically go in and register what they depend on, and it will launch the callbacks when they're ready. And like each node in the graph, it has a list of things it depends on, and it will detect when, for example, there's a recursion that is infinite by figuring out like what the problem is the idea here. And then this will help with like incremental compilation later on as well, because you'll be able to like find, okay, nodes that have changed and what they're things that depend on them, and then change those things and so on. So in this case, it's looking at, it's awaiting on a value, and then we can await on another value, and then and so on. And then we do a lookup function, for example, the lookup this will look, for example, it'll go to the pointer type, it'll look up the thing that's being pointed to, so it'll look up the thing that we're pointing to, and then it will just kind of return that. It's like what happens if you look up a pointer. And this is like how it contextually resolves things. And this probably should be fixed, but anyway, yeah, so it goes in through coroutines, and these coroutines, so for example, we're looking up an array type, it'll evaluate the expression in the array, and then it will hope that's supposed to result in a numeric literal from the like element count, and then that's the result. So now this is clearly not the correct way to do this, because this is like hard coded for 64-bit right now, and obviously I'm going to support 32-bit platforms, so there's to do stuff here, support 64-bit platforms. Okay. But that's that. Now back to the sort of syntax here. There is going to be a assembly sort of function where you can kind of add assembly procedures. So for example, this is not necessarily the exact syntax I'm going to use. I think this part's going to be changed here. But basically, for example, I would be able to say that I want to use an assembly routine. I write the assembly out like this. There's some special keywords, for example, procedure ref, so I can get I could load, for example, a pointer to a procedure for, you would say what the calling convention you want to have is, and then in addition to that, you would have the like whatever in there. So are we in standard call or fast call or whatever, and then what you want to actually reference. So that would be the main function down here. And then you could kind of do, this is not real assembly, like this is just whatever random opcodes I was using to test the assembler worked at one point. And then you could have like callable if you want to be able to actually call this from your code. Probably something like this. I'm not 100% sure that I'll keep this, but maybe something like this to like build your runtime and have like linked symbols that could be accessed from other languages, or like the ELF linker, for example, on Linux, so that it can actually like start the program. And the idea, of course, is that it's relatively deterministic. Okay. So that's the, I think, initial summary of this. I'll also be implementing these things called static tests. And the idea behind static test is basically it's just a function that gets called when you compile stuff, and then you could have your assert statements in the middle, for example, and those can cause your static test to fail, which can trigger a compilation error. Those are still being worked on, so this doesn't currently work yet. I mean, you could invoke the static test, but you can't actually, you could potentially invoke this, I believe, but you wouldn't be able to, it doesn't actually get tested yet, so that's still a work in progress. But this would execute the code same way as this, any function could be executed. Okay. So there's still a lot of things that need to be done in this language. So some of the main to-do items are going to be the global variables and, for example, string constants. And then we can add some multi-module support for importing from other modules, which should be fairly trivial. And then hopefully soon we will have a demo where you can actually kind of write some code and use it to do some I/O, like print hello world and so on. So it will require sort of assembly to get to your system calls. There's probably going to be a standard library, but that will be something that you do have to bundle up with your source code. So you would have to like basically have the standard library in the folder. One of the reasons for that is that this language is designed to do deterministic builds and reproducible builds. So that means the standard library does get bundled up with the source code to produce the binaries. So there aren't really system libraries as we know them. There may be another tool on top of that to like grab libraries from your system, for example, to bundle them up before the compiler is launched, but the actual compiler is going to be a reproducible compiler, and it will be a cross compiler. So for example, if you're using the same compiler, it will be able to produce binaries for every platform that it targets using the exact same source code, and you'll get the exact same binaries regardless of what operating system you run the compiler from. So you will have to specify your targets in here, and there's no like concept of like CPU equals native, for example, because this is a cross compiler, and it is only a cross compiler. It does not have the concept of a native target. Now I may add like another tool that will generate this module file for you based on whatever your native target is. But the compiler itself is not going to accept like the concept of a native target. You will have to specify to the compiler what your platform is and what your CPU is, and possibly like what CPU feature set you want or optimization level as well. So for example, there might be like a debug or other targets here. And then you could also put like options here that will be added in a future update. Okay, I guess that's everything for the first update, and I'm just kind of giving a general like where is this at, and what does it have so far. Okay.